All right, mathematicians, we are live with this YouTube live webinar on Chapter 11, parametric curves, vector valued functions, and polar stuff. Hope you could join us this evening. And as we are now moving to YouTube Live, or the YouTube channel, we're going to stop using the old-fashioned Google Doc, and hopefully you can all access the group chat right on the YouTube page. So we are live here again for the Chapter 11 webinar on parametric curves, vector valued functions, and polar. I'm going to go through some key tips that you need to know for the quiz tomorrow, some things that'll help you out, and then I'll also have time to take your questions. And I am scheduled to be here until 8:15. We'll run this till 8:15 the latest. However, if we're lacking viewership, or if we don't have everyone, or if everyone's already asked all their questions, then we will just end early. Okay, but my plan is to be here as long as you need me until 8:15. So we're going to go ahead and get started here in a few moments. I just want to see if people have joined us. So I want you to say hello if you're here. And let's take a look. So if you're here and in the chat box, why don't you say hello? And if not, then here's how to find the chat box. I did say I'm going to give instructions on how to find the chat box. And again, there will be a couple of bonuses. We'll have a chance for some tickets during this broadcast, and we'll have a chance to earn some tickets when I give some sample questions. But if you don't know how to join the webinar, first of all, if you're hearing this, then you've already joined the webinar. But to get to the question box or the live chat, you have to click like your icon in the top right, and you're going to have to go to YouTube, and you're going to have to set up your account there or activate it in some way or other. Okay, so hello, I see Alice is with us, and so is Julia and Tom. Who is Tom? Is this Tommy? Okay, Tommy, that's right. Okay, did not recognize the handle there, but okay, we're good to go. All right, it's good to see you, folks. It does say that there's at least one other person watching, so that they may not have been able to activate the chat box. So here's what I'm going to say: is one more warning. If you're not able to get to the chat box and you have questions that you want to ask, you can email me, and I have email open live next to me, so I can pull that up and see your questions. Hello, Tommy McBride. All right, Tommy, good to have you here. So let's proceed with this live webinar. First up, oh, no, that's not the right thing. Sorry about that. Hold on, folks. As you know, it's a live show. There's always could be technical difficulties. And here we are. First, talking about the quiz format here. It's 40 minutes. There's 6 multiple choice questions and 3 open-ended. Time is going to be important. Okay, it's not going to be one where I give you 5 of 6. I'm going to make you answer all 6 here. There are a select amount of topics, and hopefully you've studied them, but you will need to answer them all. And you need to make good use of your time so that you have time to think about the harder questions. The other ones that are quicker, more computational, you can go through quickly. You want to be able to answer those, and then you can have time to think about the more difficult questions. 2 ways to maximize your time, and we'll talk about this a lot before the AP test, but one, you want to know all your formulas. Okay, if you have to recopy that blank sheet or just go into blank notebook paper, see if you can write them down from scratch without looking at any notes. If you can do that in 2 minutes, that truly shows that you know them. You got to know your formulas quickly, because if I ask for an acceleration vector or the total distance traveled by a particle or something else, you don't want to have to spend a lot of time remembering the formula. The formula you want to have right away, and then you can go right into doing the work. Secondly, you want to use good calculator techniques. I'm going to talk more about that in a second, but um, practice using your calculator. You should know where the integrals are, derivatives, graphing. You should be able to find zeros, etc., and you want to be able to do that efficiently. Two ways of solving equations with a TI calculator. I just want to bring this up specifically because it's thrown some of you for a loop on a quiz or test here or there, and even in class when we're like, oh, let's use the solve key, and then it doesn't work. So you can use the algebra solve key, but there's no guarantee that that's going to work for you unless, sorry, one second. There's no guarantee that's going to work for you, and I would suggest graphing and finding the zeros if there's any question about it. So sorry, one second. I just had to take an important message for a second that threw me off. Let me just say what I was going to say. You can use the solve key if it's an algebraic equation, if it's polynomials, even if it's rational expressions. It will be good at solving and it will solve efficiently and quickly. However, once there's trig involved, once there's logs, once there's other more complicated things, that solve key is not going to be a guarantee. Yes, it might work here or there, but it's not a guarantee. So the guarantee, however, is to graph the function and find the zeros. So you're going to have to isolate the dependent variable, make it y equals of some sort. That might require some manipulation. Or you can just graph it right away and then set one side equal to 0, do y equals, and then find the zeros. That's what I would suggest to solve the equation. That's going to be guaranteed to work. I know it might take a little longer, but with practice you can do it quickly, and you're not going to be stuck with the solve key calculator trouble where it sometimes will not work. Oh wow. Okay, so it's time for sample question number 1. I meant to give you more warning. I just kind of flashed it on the screen. Here's how this is going to work. If you are the first person, okay, Eric says hi in the chat box. Hello to Eric. Shout out to Mr. Khan of the Future Khan Academy, perhaps. So Eric, you'll be with us for this question here. The way this is going to work is I'm going to put the question up, and the first person to get the answer with some brief justification will receive a ticket. Board point counting towards the 4th marking period, not the 3rd. So I hope you're ready for the question. Here it is. You might need to zoom in or go full screen. You might need to have a calculator nearby. And this is the question. Good luck. So again, this is our first sample question with a board point to the first correct answer, and it will be awarded for brief correct answer with brief justification as well. Take your time. Hope you got pencil and paper handy. A chance to earn a board point. Okay, so I'm waiting for some responses. Those of you joining us late, if anybody's joining us late, and in order to get the board point, I see an answer there, Tommy, but you got to have a brief justification, some explanation. Okay. All right. Okay. I'm going to say that is insufficient justification. We're missing a key part of this, and it might be a little different because I know in class we're used to thinking of horizontal and vertical tangent lines, and Tommy is a pretty good answer up there, but it needs to take something else into account here. We want to know when this particle is at rest with respect to time. So let me just start by saying Tommy's answer, the A is correct. Okay, you need to have dy dt equal to 0, but the justification is not entirely sufficient. You need to bring some other factor in. Right. Yes, I see. I know. I see what he's saying there. This does bring about a confusion. I'll just see. I'm gonna wait one more second and see if anyone else can pick up the nuance here. And if not, and Tommy's got the best answer, then I will award him the ticket. But I just want to see if anyone else can come up with the nuance that makes the justification not entirely correct. We'll just wait another 10, 20 seconds. Okay. Anyone else have an idea? Okay. So you're both saying the same thing, Eric. That was a nice, concise way of summing up what Tommy said, but I will say he did state that already. Um, so let me be nuanced here with my response. A is the correct answer. However, there's a difference between dy dx and the particle being at rest. Okay, dy dx will give you the slope of the tangent line of the parametric curve. And this is a nuance that didn't quite come up in our class discussion, though it may have come up on your homework. Dy dx will give you the slope of the tangent line to the parametric curve. However, if you want to know when it's at rest with respect to time, you want dy dt to be 0, but you also need dx dt to be 0. In other words, this particle can't be moving in the y direction, but it also can't be moving in the x direction. And you can definitely envision a scenario where the particle was moving with respect to y. I'm sorry, it was not moving with respect to y, but it was moving with respect to t. In fact, you can probably picture that. Sorry, with respect to x. It's moving along, let's say, the x-axis. And there, yes, the tangent line would have a slope of 0. But the point is that the particle could still be in motion and not at rest. So the full answer would be to say that it's A, because both dx dt and dy dt are 0 when t equals 2. Okay, so hopefully that nuance will help you out there. Again, we're drawing a distinction between dy dx, which will give you the slope of the tangent line of the parametric curve, and dx dt and dy dt, which give you the rate with respect to time, or with respect to t, whatever that parameter is, at which it's moving in the x direction and the y direction. So due to the fact that Tommy was first there with the answer, though Mr. Khan had a nice summary, I will say I will award 1 ticket to Mr. McBride, but I do want you to have that full explanation under your belt, because there's another choice here. There's another choice here. Let's see, what was the choice? I guess no, yeah, that was the only candidate. I'm trying to think if there's another choice that had dy dt as 0, but it didn't make dx dt 0. That would be enticing, but it would not be correct. We have another sample question for a board point. Ready? It's on the next page. This one is open-ended. You will need a calculator. Okay, it does involve polar, if I remember correctly. Yes, I think it involves polar. So let me get my answers out, and I will award a board point to the first person with the correct answer on this question. So this is sample question number 2. You may proceed when you are ready. And if you're just joining us, this is all taking place on the live webinar. So if you're struggling to use the chat box, feel free to email me your question. But you do have to go to YouTube Live, or just YouTube, and activate your account. And then you should see the chat box right to the top right of the screen. This will be our last sample question, and then we're going to go to the your questions and answers. I have my textbook nearby. Pull up the sketch pad, and we'll talk about any questions that gave us some issues. Let's go to Sketchpad. Okay, hopefully you're still working hard on this problem additions. We still don't have any answers yet, but I will award a board point to the first correct answer. I mean, if like 5 minutes passes and nobody gets this one, then I can explain. Okay, we see, oh, we got two similar answers there of 2 pi. And I just double checked my answer, and it is not 2 pi. Go ahead and try that again. Just see if there's any other answers, and then we'll talk about this one on Sketchpad. I will draw it out for you because having a sketch in mind is going to be crucial to this one, and perhaps even drawing one of those translation sketches will help you. Okay, so we're waiting on some other answers. Any other answers to this open-ended question? And in the meantime, if you're just joining us, we are using the chat box to type questions and talk about different methods. Okay, going once, going twice. I'll keep working. Let me ask a question. Is anyone still working? If you're working, then indicate yes, and I will not reveal the answer yet. But if no one is working on this problem still, then we can start to talk about the correct answer. No, Tommy, that's not allowed. But you're allowed to say you're no longer working. Is anyone still working? Going once? Going twice? And sold. Okay, let's talk about the solution. I'm curious what you did. Maybe you folks can explain to me. I have a feeling there might have been an error in the bounds, but we can talk about it together. So let me, hold on, I have to switch the view for a second. Let's see, stops, screen sharing. Oh my gosh, hello folks. Hope you're doing well. Let me want this one. Okay, so this is my Desmos graph of the function, but since you don't have Desmos available to you, at your fingertips, let's talk about how we can get that graph. It is, let's see, y equals 2 cosine 3 theta, or actually it should be r equals. Okay, so if we graph this periodic function, we know it's a sine wave, so it goes from 2 to -2. The period, and this is crucial, is is 2 pi over 3. 2 pi over this first coefficient. Okay, so that means after that, we're going to be able to complete one full cycle. In other words, cosine will go exactly like something like that. Okay, I guess it's an approximate. And then it'll keep going. The next one will be a 4 pi over 3. Excuse the crude nature of the graph. Still not an expert at drawing with this mouse. But here we are. So how does this translate to the polar graph? 3-petaled rows. Well, we know we start at 2. And then by the time we get to, this is pi over 3, half the period. So this is pi over 6. By the time we get to pi over 6, we're already at 0. So that's going to form half our rows to start off. Then by the time we get to pi over 3, we're at -2. So pi over 3 would be here, but we're in the negative direction. So that would be down here. Pi over 3 negative, it's about something like that. And then it's going to loop back to here. This will be pi over 2, but in the negative direction, because it's really pi over 3, and then you add another pi over 6. That's the step size. So that'll be 3 pi over 6, which is pi over 2. So pi over 2 in the negative direction should be here. So we're heading towards that. So it looks like my rows. I don't like my rows. My rows is not turning out too well. But pi over 3 is here, and then it's going to loop back to pi over 2 there. And then pi over 2 up to 2 pi over 3, or back up to 2. 2 pi over 3 is about 120 degrees, or pi over 6, pi over 3 times 2. And then we're going to loop back here, take another pi over 6, and we're back to 0. Brings us here, and then we loop down. This would be, let's see, 2 pi over 3 is 4 pi over 6. We had a 5 pi over 6. That's this. And then we had another pi over 6, and we are at pi. So by the time I get to pi, which is over here, we're at -2. So -2 would be that direction, so it's going to loop back here. And the rows is traversed with a pi as we go up to pi. Okay. Going to pi completes the rows, is what I'm trying to say. And so what you should have typed in your calculators is pi r squared, the area of the circle, minus the area of the rows. And the area of the rows, 3-petal rows, is, well, I'll put the 1/2 on the outside. That's usually what they're doing on the AP test. 1/2, and then the integral is from 0 to pi of the function 2 cosine. And I'm going to see if you have any comments in the chat box. 3 theta squared d theta. And when I plug this into my calculator, I got about 9.425. I'm not positive, but I have a feeling the common mistake might have been with this upper bound, assuming that was 2 pi, which it is not. Okay. Eric is talking about buying and selling. Let's get this back on topic here. But any other questions about that explanation? What mistake did we make? And then I'm going to move on to your questions and answers. But I think this was a good question because it gives you a sense for, what we could ask on an open-ended to find area, at least part of an open-ended question, and you got to, track these things and get a good answer from your calculator. Okay, so that being said, I am going to switch it up to your questions and answers. Thank you for watching, and we'll turn it over to you for any questions and answers. You can put those right in the chat box, and I will make sure to get right to those. So what questions do you have on polar or parametric or vector valued functions? I have a textbook handy that I can look up. Questions nearby. Anything you had? Okay, bounds, yes. Okay, Alice is raising an important question here. Why can't you solve the problem? That's a good question. By finding the intersection of the graphs and then multiply that answer by 3. I think you can assume those 3 sections are equal, Alice, but I'm not sure what you mean. The intersections, are you talking about where the rose petals hit the circle? Because I guess the point would be, well, you still need to know, the area of one, you got to find the area of one of those rose petals. Okay, yes, I think you're talking about those petal tips. Like, for example, if you found out that the one petal hits at 2 pi over 3, right, 2 pi over 3, what you're really finding there, yeah, I see what you're saying, Alice, that's a good point. Let's draw this out because I think that'll help explain this. When you say 0 to 2 pi over 3, you're finding the area between 2 pi over 3 and the origin, so that's really just a straight line, 2 pi over 3. And you're finding the area of this sector. Okay, when you go 0 to 2 pi over 3, oh, actually, no, you're not. No, you're not. I'm sorry, that's not right. That would be just if you were integrating, if you were just integrating theta, but you're not. You're doing the function. So that the reason is because of how I traced the rows. The rows went to here, and then it went to here. So 0 to 2 pi over 3 is actually not, it's not the area of an enclosed region. Okay, because where does the 2 pi over 3 go? When you're talking about the rows, if you look at my sketch before, 2 cosine 3 theta, let's talk about this again. It goes to here, pi over 3, it's down to 0. And then actually, it's not down to 0. I lost my sketch from the other part. That's the answer. Let me use Desmos for now, but you can go back and replay my sketch, my translating. I couldn't remember it just now from memory. But Desmos, here's what it shows you. If I go 0 to 2 pi over 3, that's the area you're finding. So you're finding one petal and a bit more, actually, because you got those other 2 half petals. So it actually, well, it looks like if you take that full petal and 2 half petals, if you multiply that answer by, instead of multiplying by 3, I think if you multiply it by 1.5, right, because it looks like you got 2 out of the 3 rose petals, I think it should work. Try your answer times 1.5, then subtract from 4 pi. But I think that Desmos graph is the answer to your question. When you go to 2 pi over 3, that's what you're graphing. And how would you know that? Well, the only way to truly know that is to make one of those translation sketches. And I know they're a little annoying and they take some practice, but that's where they could be important so you know exactly how much of this curve you're going through. At this point, they might be checking that times 1.5, but you can open up, I'll open up the floor to other questions that you may have had, and any questions from this section, chapter 11, any sort, whether it's homework or other things. I got the textbook open here. I can also recommend to you the study guide free response question. That's a good one if you haven't tried yet. Okay, good question from Julia. What's the difference between the length of a parametric curve and the total distance a particle travels along the parametric curve? The distance is in your perspective. Mathematically, they are equivalent. In fact, we'll use the same formula for both. But when we're talking about the length of a parametric curve, we don't technically have to be talking about a particle moving along it. We can just talk about a curve that's defined with some parameter t. And that parameter technically does not have to mean time for some actual particle. It's just a third parameter in the abstract. And so we can find the distance of the curve by taking the square of the sum of the squares of the derivative components without actually talking about time. Okay, but the total distance a particle travels along a curve, it comes out to the same thing, but we'll specifically be talking about time. So I'll say mathematically, those are equivalent, but it'll depend on the context and your perspective of what you're trying to find. But as far as formulas are concerned, the formulas are the same. Eric asked, I went from 0 to pi over 6 because pi over 6 is the next time r is 0, and that gets you half a petal, and you can multiply by 6. Wow. Eric, this is a good idea. Did that work for you? And then Tommy, I see you've raised a separate question. So we can talk about that. Okay, Tommy said, for number 14 on the chapter review, why is the answer 0, -9 instead of that? Okay. Let's look at that one. Sorry, I'm flipping to that. Let's take a look. Hold on. One moment. Okay, so Tommy's saying number 9. Okay, Eric, we will go back to that question in a moment. First, let's look at number 14 on the chapter review. Find the points at which the tangent to the curve is horizontal instead of just 0, -9. Okay, so let's look at that one on the sketch pad. This is number 14. Oops. Asked for by Tommy. And it says we have two components. We have 4 cosine t. That's x equals. And y equals 9 sine t. And the question is, when is the tangent to the curve horizontal? So there we're looking for when dy dx equals 0. When does that happen? Okay, so let's find dy dx. I know you might have already done this, but let's just go through it. Dy dt would be 9 cosine t. Dx dt would be -4 sine t. So the question is, when does this equal 0? So let's set 9 cosine t equal to 0. Or, I mean, it's really this fraction, but this fraction will be 0 when the numerator is 0 and the denominator is a number. So we get 9 cosine t. So we're really asking, when is cosine t equal to 0? And that's going to be at pi over 2 or 3 pi over 2. Okay. And then if we plug those into the original equations, pi over 2 for cosine, it's going to give us 0, but pi over 2 for sine is going to give us, pi over 2 will give us 1, whereas 3 pi over 2 would give us -1. So this one will lead to 0, 9, and this one will lead to 0, -9. And in fact, since they don't provide a interval, we would technically need to keep going. I mean, this could be any multiple, any odd multiple, k pi over 2, where k is odd. However, you're not going to get any different answers than those two. Does that make sense? Okay, hopefully, Tommy, that makes some sense. Let's go back to what Eric said, and anyone else who has another question, feel free to drop it in. I noticed it's, wow, time went a little quick there. Sorry for any technical difficulties that delayed things, but we got another 15 minutes on the clock. I would love to answer some more of your questions. And let's think about Eric's for a moment. Okay, I'm going to actually check this integral, Eric, on my calculator. Maybe it's a calculator error. But as you go from 0 to pi over 6, and then we multiply it by 0.5. Okay. Okay. Let's see. And then any other questions you had, feel free to send them along from the textbook. So we're thinking about Eric's question here. Eric said, it's a good objection. And so we're thinking about if his method works, and if not, why doesn't it work? So it says he went from 0 to pi over 6 because pi over 6 is the next time r is 0. And that gets you half a pedal that you can multiply by 6. And I agree that makes sense. One thing it does assume is that the pedals are symmetrical. And well, I do think that's true. It may not always be the case. So hold on, let me just double check your calculation first. So we do 4 pi minus, this would be 6 of those, 6 times, or let's do, put parentheses in all the right places. Then we have a 1/2. Okay. Yeah, I did not get an answer that was the same. But I also didn't get just 2 pi. I got 6.286 when I'm doing your method, Eric. So that's a good question. Oh, you know what? I typed it in my calculator wrong. Uh-oh. Did I do that the other time? Oh boy. Yeah, Eric, it works. It works. I typed it in my calculator wrong. So you got to make sure you have all those components correct. So Eric's method works, which is good because even though we were assuming the pedals were symmetrical, I thought that was a valid assumption. What you do, Eric, what you got to plug in is 4 pi. Man, I'm pumped that worked out. Minus, and then we're taking 6 pedals. What's a pedal? 6 times the pedal. Pedal is 1/2 integral. You did this, or sorry, 6 half pedals. 0 to pi over 6. That was your intuition there to see that the pi over 6 was half a pedal. And then you do the full function. Make sure you got 2 cosine. My mistake was I didn't put the 3 and 3 theta. Make sure you got 2 cosine 3 theta. Square it up, d theta. Plug all this in. You will get the correct answer, about 9.245. So that is a valid method after all. Mr. DeRosa, okay. My calculator got a board point, says Tommy. I'd have to agree at this point. Well, actually, no. My calculator didn't correct the mistake. The calculator, I put it wrong into the calculator. Okay, Eric, nice work. That is another way to think about it with polar curves and symmetry. Any other questions on parametric or polar? I know you folks only had a few questions tonight, so maybe that means you've tried a bunch and you feel confident, or you still have to work through some problems. My recommendation would be to do the study guide FRQ, some other questions from the review, and make sure you're comfortable with all the formulas and how to use your calculator. Are there any other questions? Participants going once? Because I don't mind ending a little bit early if you have no more questions, but I can stay here till 8:15 if someone has a question. So any other questions going once? Going twice? Okay, Julia, just in the last second there. Good question. How to find the bounds in general? Sure. Let's talk about it. Let's say you want to find the area enclosed by 3 sine of 2 theta. Okay. You want to find the area enclosed by r equals 3 sine of 2 theta. Now, the long answer is to find the bounds, you have to think of where your curve is starting and stopping. How do you know where your curve is starting and stopping? You're going to have some sense of translating the graph from a periodic to a polar. One way you can get around that, if you're very nifty with the calculator, you can plug this into the calculator with alternative bounds. In other words, suppose I go to Desmos here. Let's see. I don't know what this is going to look like. 2 sine, or what did I say? 3 sine of 2 theta. Some people have formulas memorized. I do not have those. And then you go to your calculator and you say, okay, first I'll go to pi over 6. Okay, that doesn't fill the curve. And then I can go to pi over 3. All right, that's not filling it. I can go to pi over 4, pi over 2. Well, I can go to pi. Maybe I'll go to 2 pi. Oh my gosh, maybe I'll go to 3 pi, see if there's more to the curve that I can't see. No, there's no more to the curve than 2 pi. Well, maybe I didn't need all of that 2 pi, 3 pi over 2. Well, that doesn't get me all the graph. So it turns out 2 pi does give me the full graph. So if I wanted all the area enclosed, I would have to go 0 to 2 pi, it turns out, in this case. So one way is you can guess and check bounds on the calculator. You can plug in a few bounds and see if it gets you the full curve. If it doesn't, you can go here and do the translation graph. That's what we've been practicing in class. And you'd have to go through the full sketch. And then you'd see after 2 pi, I end up with my full graph. So in general, that's how I would do it. I would actually use the translation graph. Here I have a period of pi. So I know pi, I get through a sine wave. up, down, up. And then I would translate that. By the time I get to pi over 4, I'm at 3. And then by the time I get to pi over 2, I'm back to 0. By the time I get to, so this is pi over 2. By the time I get to 3 pi over 4, I'm at -2. 3 pi over 4 is here, but then negative will be over here. And then by the time I get to pi, I'm at 0 from the negative direction. And then this curve will keep going until you finish it. Okay, so that's how I would do it. That's how I would sketch it. Tommy asked a good question. Okay, bounds on the TI-89. Ooh. Unfortunately, Tommy, I apologize. I don't have my TI-89 handy, but let me see if I can get that information for you. And I will blame Manish because he has my TI-89. No, I can't blame Manish. His actually broke, the one I lent him earlier, so I lent him mine. You know what, Tommy? Let me get back to you with an email, okay? Because I'm gonna have to look at it online, and I'll either find a video or a picture that shows where to put in those bounds. But I'm sure you can do it. And I just have my Inspire with me, so I don't know off the top of my head. But Tommy, I will check and send out an email. Okay. Thank you, Julia, for that last question. That does bring us to 8:15. So I am going to say thank you very much for joining us on this webinar. Have a good night. Happy studies. And if you want to pop in the morning at 7:45, 7:50, I'll be there if you want to ask a quick question. Oh, Tom, you think you found out? You go to the window and then change the bounds for theta. Yes, that's a winner. That sounds right. Go to the window and you'll be able to change the bounds. So a little bit different than parametric, but you should be able to do it. Okay. Thanks a lot, everyone. Thanks for joining us on this webinar. Hope it was a help to you, at least somewhat, and have a great night. See you tomorrow. Bye-bye.